días a todos, bienvenidos al seminario del día de hoy. El día de hoy tenemos el gusto de tener a la doctora Sara Bonacchi del Departamento de Chemistry de la Universidad de Padova en Italia, quien nos va a hablar acerca del tema Designing Tunable Luminescent Materials from Atomic Level Control to Molecular Self-Assembly. Quickly, Dr. Sara studied and received in 2009 the PhD in chemistry from University of Bologna. And in 2013, she joined the group of Professor Paolo Samori in Strasbourg, in France. And then currently she's an assistant professor at the Department of Chemistry of the University of Padova within the Molecular Electrochemistry and Nanosystem group led by Professor Maran. Her current research focus on atomically precise metal nanoclusters to generate strongly coupled materials with peculiar optical and electrochemical properties. So, thank you very much, Sara, for accepting our invitation. And now, the floor is yours.
Okay, thank you. Good morning, everybody. And of course, first of all, I would like to thank the scientific community for this invitation and Eduardo for his kind introduction. So let's start with my talk today, and actually it's a long journey along the designing of tunable luminescence material. In particular, I decided to divide my talk today in 3 different topics by taking into account the dimension of the dyes or luminescent molecule or nanostructure I deal with. And in particular, I would like to show you how we can use molecules as supermolecular building block to assemble photoresponsive 2D material working with something very, let's say, small, around 0.1 nanometers, so in the molecular size, and as we can use this molecule as building block to match amazing lattice structure. And then we pass to something a little bit bigger, so like the atomically precise metal nanocluster, and I'll show you as we can play with this little bigger structure to create emitting dyes. And then I will end my presentation with something a bit more bigger, let's say, in the size of a nanoparticle, and I will talk on dye-doped silica nanoparticle. So let's with this journey with my photoresponsive 2D material. So, and so for the people you that is not familiar with van der Waals heterostructure, we have to consider that when we talk about van der Waals material, we're talking about something like a graphite or transition metal dechalcogenized, and whose properties are very different when we pass from the bulk material to the monolayer. Is that, as you know, starting from the Nobel Prize in 2011, especially the physics committee, start to be very interested in this 2D material, and whose properties are very affected by the fact to be monolayer. So Nozelov got the Nobel Prize because he was able to use this Scotch tape approach to form a monolayer film of this 2D material. This monolayer film has properties that are strongly different from the bulky. As you can see here, for instance, molybdenum sulfide in the monolayer film is bright. Instead, the 2 or 3 layers are totally dark. And for physics, this open a plenary of different kind of research activity, working with different kind of 2D material, a sort of new library from their community. And in particular, they also use the possibility to create van der Waals heterostructure in order to place with different kind of 2D material to create novel function and novel function material with higher optical and electronic properties. But as chemists, we were wondering how we can play with this fascinating 2D material, and in particular, how we can tune the properties, the electrical and optical properties of these two materials by playing with these two dimension and molecule at the same time. And our approach was something that I create during my postdoc at the University of Strasbourg in the group of Samori. Our approach was to use high-order assembly supramolecular molecule in order to create a sort of lattice, high-order supramolecular lattice on top of a 2D material, and use this high-order molecule to tune the conductive properties of the graphene and of the graphene layer. In particular, what I would like to show you today is in this scenario, in this kind of research field, and also to do a step further. So not only to use a molecule to create a supramolecular assembled molecule to tune, to induce an effect on the electrical and optical properties of a 2D material, but the possibility to use switchable layer to switch in real time and in situ the properties of graphene of other kind of transition metal chalcogenide. And in particular, we select among different photoswitchable molecule, the spiropyrene unit, and in collaboration with Professor Stefan Hecht at the Humboldt University of Berlin, we designed this spiropyrene molecule with this long alkyl chain here, 18C atom, in order to induce a stronger van der Waals interaction among this alkyl chain in order to create a stable and stronger lattice on top of the material. So we designed this kind of spiropyrene molecule, and we try to understand if we can use this photoswitchable unit from spiro to merocyanine and then back to the spiroform to induce a photoswitchable tuning optical and electrical properties of this van der Waals heterostructure. And so basically we use a quite simple approach. So we spin coat spiropyrene on top of a graphene layer, or also molybdenum disulfide layer. And first of all, we observe if it's still possible to photoswitch and dry this spiropyrene molecule, and it's indeed, as you can see here, we were able to photoswitch the spiropyrene from the on top of graphene from the closed form to the zwitterionic form, and go back and further for different cycles. So this for sure for one of our first achievements, so the possibility to still induce a photoswitching of this molecule even if we are working on dry system, and if these molecules are on top of 2D flakes. We also perform STM images to observe how this molecule assemble on top of graphene as well as on top of MOS2. And as you can see here, we observe the possibility to not only observe the assemble of this spiropyrene, so the closed form on top of graphene, but also the possibility to irradiate in situ, so to shed UV light on top of this dry film and observe the modification of the assemble on top of graphene by means of STM, and then back with the thermal relaxation back to the original form. So this was actually one of the first proof of the possibility to work with this highly ordered lattice structure on top of 2D material, the possibility to observe their ordered film, and also the possibility to tune their assemble in situ by playing with light. And we also perform XPS analysis to prove the tuning of the photoswitchable molecule. So the closed form to the open one, you can clearly see the modification of the binding energy of a nitrogen atom from the closed one to the zwitterionic one, to the charged one, and then back again to the closed one. So another proof that actually we were really able to switch in situ and real time our photoswitchable molecule on top of the graphene layer. So not only we are able to form high-ordered film, but we are also again able to switch the properties of this molecule. And to understand how these two different forces, so the closed one and the zwitterionic one, the charged one, and in case induce and dipole moment on the graphene layer on which we are assembled, we also perform molecular dynamic simulation and density functional theory calculation that prove actually that the spiropyrene form, even if it is able to form an assembled lattice, that there is not a real dipole moment on top of graphene. Instead, as soon as we analyze the merocyanine form, the open, we observe a significant and strong dipole moment oriented perpendicular to the substrate. So to prove if this kind of approach, so the possibility to use molecule like building block to create a photoswitchable lattice on top of a 2D material, and if this kind of photoswitchable assembly can induce actually an electrical modification of the graphene, we perform field effect transistor analysis, and in particular for people who are not in this field, actually basically we apply a voltage and we measure the current on top of the film. And what we observe actually is indeed as soon as we spin coil our spiropyrene molecule on top of graphene, there is not really an effect on the Dirac point of graphene. That means that actually the moiety can, even if it is able to form a high-order lattice assemble on top of graphene, is not able to induce any kind of effect on the electrical properties of the graphene below. But as soon as we shed UV light on this film, again on the dry film, as soon as we shed UV light on this film, we observe a very strong endopic effect, so a very strong shift negative voltage of the Dirac point of graphene, and we were also able to go back upon visible light. So we were actually able to prove, thanks to this field effect transistor measurement, the possibility to play with molecule, high order assembly molecule, and to play with light for switch the electrical properties of 2D material. And to confirm this result, we also perform UV photoemission spectroscopy in order to estimate the work function of the two molecules, so the spiroform and the meroform, and to confirm the doping effect we observe in a field effect transistor with the photoemission spectroscopy. So we for the first time, we observe a photoswitchable N-type doping of 2D material just by playing with molecule, and it was also very interesting, and at least to our opinion, the possibility to use an optical microscope setup to decide how much we want to change the electrical properties of the thin flakes. Here, this is the device, this is the gold electrode, and if we induce a doping, if you induce a photoswitch all around the graphene flakes below here, for instance, as you can see my pointer, we can totally induce a switch in the electric properties, so a totally n-doped effect on the graphene flakes. But if we partially switch the pyropyrene molecule on top of graphene by playing with the microscope setup in this other direction, you can clearly see for the transistor result, that we can partially tune the electrical properties of a graphene flakes. And this is really a result of two different assembles of a graphene, as you can see here from this STM analysis. So with this approach, actually, we were able to show the possibility to play with the same simple molecule and with a supramolecular approach, first to create a higher order assembled molecule, and then to induce different kind of dipole moment on top of graphene, and then induce a strong effect on the electrical properties of a 2D material. And this result was true not only for graphene, but also for different kind of van der Waals heterostructure like MOS2. And we are in the Paolo Samegri group, we are still working on this kind of topic by playing with different kinds of tunable material and different kind of tunable photoswitchable molecules. So this for sure opened the way to the possibility to also for chemist people like me, for instance, to play with this 2D material and to induce strange effects on this material just by playing with light and photoswitchable molecule, just by select the photoswitchable dyes able to induce a strong dipole effect and order a dipole effect on the 2D material. I would like to go a little bit further, so increase a little bit the size, not anymore molecule, but atomically precise metal nanocluster. That actually is the topic, as Eduardo says, is the topic I'm deal here in Padua. So metal nanocluster. So basically nowadays it's possible to synthesize monolayer protector cluster in atomically precise ways, which means that its structure and its chemical properties are well known and well defined. Basically by means single X-ray crystal structure, NMR, and mass spectrometer, is possible to identify the structure of this metal cluster in an atomically precise way. And moreover, thanks to their tiny dimension, we are talking about around 1 nanometer, 1.8 nanometer, they are characterized by confined property, optical and electrochemical properties, so they show peculiar molecular properties. And the interest, as you can see here in this sort of cartoon, of the scientific community is increasing a lot in this last year. Why they are so interested? Of course, we have to clarify that this metal nanocluster, first of all, we have to clarify that these metal nanoclusters are basically, we can consider as they have a double nature, a hard, soft, let's say, nature. So, for instance, here I report one of a benchmark nanocluster, the goal 25 nanocluster, surrounded by tile, 18 tile, and this kind of cluster, like the others, are all characterized by an hard core, an hard core made of metallic core, surrounded by a soft and dynamic organic like in this case are tile, but can also be carbene or phosphine ligand that stabilize the cluster, they protect the cluster, and also give them different functionality. So this double hard soft nature of the cluster are very fascinating, and in particular the more fascinating aspect in this field is the possibility to really tune atom after atom the and optical properties of this cluster. So basically we can really change one single ligand or one single metal atom in the core, and in this way we can dramatically change the physicochemical properties of this cluster in a way in which there is a stronger property relationship. So we are sort of magicians that we can play with this structure to tune their optical and electrochemical properties as well. And just to give you an example, for instance, if you look at the size effect, for instance, starting from the smaller gold to the bigger 145 cluster, you can clearly see that, and here a result obtained in our group here in Padova. You can clearly see that the gold 25 has a molecular behavior with very nice, we report this very nice DPV curve in which you can clearly observe a well-defined HOMO-LUMO gap. Instead, as soon as you start to increase the size of this cluster up to one of the bigger one, 144, you lost this molecular behavior. You are going to the double layer charging behavior. So a size just 0.5, 0.7 nanometer of the diameter can dramatically change the electrochemical behavior of this cluster. And another intriguing aspect, to me at least, is the possibility to really change the one metal atom in the kernel, so not anymore the size, so the same kind of size, the same kind of core structure, but with different metal doping, so with different metal ion, you can clearly change the electrochemical properties of this cluster. So you can play actually with the metal doping effect, to modify the kernel but not the structure, and to induce a dramatic change in their electrochemical properties. So again, in a philosophy which each atom counts in the physicochemical properties of this cluster. And even if the structure, let's say, and the electrochemical properties of this kind of cluster, this big cluster, are nowadays well known, as soon as we start to talk about photoluminescent properties of a cluster, there are still lots of open questions, in particular still challenging question of the origin of the mechanism of the cluster are still under debate in the community. But also, if you think about where this nanocluster emit, is still not clear at all. Just to explain why there is so many, in some cases, even mistake or doubt about the photoluminescent properties of this cluster, I would like to show you these three different emission spectra, and that if you look at this, they look like the emission of three different species, but instead they are the emission of the same kind of gold 25 cluster obtained by using the same kind of fluorimeter, but just playing with three different photomultiplier. And this example is to show you that since the emission of gold nanocluster in general are in the range of the near infrared region, you surely know that this region is very hard to detect. And if you don't use the proper PMT detector, you can see different kind of maximum, different kind of shape, just because you are using, let's say, wrong eyes to observe your cluster. And this creates in this community a lot of misunderstanding and a lot of mistake if you check in the literature. And to overcome this problem, we really think that the combination of the best of the best world, like optical spectroscopy and chemistry, could really help to solve this problem. And for proof that, we perform spectroelectrochemistry on this cluster, in particular on gold 25 cluster. And to do that, we optimize the spectroelectrochemical setup, and basically needs quartz cells. And I would like to stress that we are using a very thin film actile layer in order to minimize the diffusion layer in front of the work electrode that was made of a platinum grid. And we use with this setup to perform CV-core, and here I report the CV-core of gold 25's Manus. It's a very nice CV-core that respects the electrical property I showed you before. And then we use this setup, first of all, to perform UV optical spectroelectrochemistry analysis. And as you can see here, even if these kind of clusters are very broad absorption band that basically cover all the UV visible range, starting from 800, 900 till 300 nanometer, the optical spectra has actually different kind of fingerprint feature in function of the charge electrode, in function of the charge of a cluster. You can indeed see that you can indeed, for instance, this maximum that change starting from the neutral one to the -1 and the +1. So even if we have to have like a good eyes, as soon as you start to work with this kind of a material, you can use the UV visible optical spectra like fingerprint to understand if you are which kind of cluster you are working with. And I would like also to point out here that the gold 25 neutral form is a radical form that is very peculiar, and it also have an interesting aspect when you work about magnetic properties of a cluster. However, we perform first the spectroelectrochemical analysis of the optical properties of this cluster, and then we use the same kind of approach to perform fluorescence spectroelectrochemistry. And what we found out, so we used this setup inside a spectrofluorimeter equipped with a near-infrared detector, sensible up to 107 nanometer. And what we obtain is, as soon as we start to apply a potential starting from negative one toward a more positive one in the time, we collect this Pauling fluorescence spectroelectrochemical spectrum, in which we can observe that the -1 form is characterized by a maximum at around 180 nanometer. As soon as you apply a positive potential, we observe a decrease in the emission and a blue shift up to around 900 nanometers that correspond to the neutral form. And this is, for instance, the first clear identification of the two different charged form of this kind of cluster with a well-identified emission spectra and with a very interesting 100 nanometer shift between the -1 to the neutral form. And if we go further, we apply even a more positive potential, we observe instead an increase of the emission without any more without shift in the emission. So again, the possibility to clearly identify the neutral form with the plus form in function of their quantum efficiency, basically. Just playing, and we obtain this just playing with the electrochemical potential inside our spectroelectrochemical setup. To prove that these results are really corresponding to the three different charged gold 25 cluster, we repeat the same kind of experiment by using a standard cuvette, so a standard approach inside our spectrophotometer, and we use a chemical oxidation to have the 3D -0 and plus form, and as you can see, this photoluminescent spectra really match the one that we obtain by means of the spectroelectrochemical setup. And this is the first proof of these three different charged gold 25 emission. We also proved that the possibility to play with the charge for playing with the emission properties of the cluster, and also the fact that we have the possibility to play with the atomically precise structure with very high stock shift, because if you consider we can excite this system at around 400 nanometer, and we have an emission in the strong near infrared region that could be very useful if you think about image bio application. We also perform time-resolved spectroelectrochemical analysis just to prove a possibility to switch between the neutral form and the -1 form, and we perform for this purpose multi-pulse chronoamperometry measurement. And as you can see, there is a perfect match between the current, the density current, and the emission then that can be switch on and off if you look at 180 nanometers. So you can really switch real time the emission of a neutral form in near infrared region. And I think it's very, this work is ongoing, but it's a very first example of spectroelectrochemical analysis of this kind of cluster in the near infrared region. And we also think that it could be very useful to understand the origin of this of the emission of this cluster that is still, as I said before, under debate. As I said before, in this kind of structure, each atom counts, and I would like to show the effect of the metal core, because till now I talk about gold cluster, but if you change metal, so not more gold, but you use copper, you can obtain similar structure. For instance, here we have a copper 5 core metal cluster, so a smaller like in size, with a zwitterionic tile, which is a very stable cluster. And what we observe that this kind of cluster can act actually like a molecular thermometer. Indeed, if you look at the photophysical properties of this cluster, you observe that a room temperature is characterized by a very broad emission then, centered at around 700 nanometer. In this case, copper and smaller cluster has an emission more in the visible range instead of a near infrared region. However, it's characterized by very nice emission then. But as soon as you decrease the temperature, so you reach 77 Kelvin, for instance, you observe a red shift, a narrowing, and also very important, you change more than 2 orders of magnitude the lifetime of the cluster, passing from 500 nanosecond up to 40 microsecond like lifetime. And what it was very interesting to us, it was to observe that these photophysical properties are not affected neither by the solvent nor by the presence of the oxygen. And we then decide to go inside this optical behavior, and we perform analysis on the optical properties of this cluster in function of the temperature. And here I report the actual effect. So you can clearly see that going from lower temperature up to higher temperature, you observe a decrease in the emission as well of the lifetime emission lifetime. And if you plot these results as a random plot, you can clearly see a linear trend in a very huge and broad range of a temperature between -45 up to 45 degrees, and you can clearly also detect change in the temperature lower than 0.1 degree. So actually this kind of cluster really acts like molecular thermometer. So you can really use this kind of material to feel different temperature in a very broad range and with a very high sensitivity. This is, let's say, not the end of the story, because we also try to understand the origin of this peculiar behavior, and so we perform time-dependent density and functionality theory, and we observed actually that the LUMO is centered, but the LUMOS +1 is more ligand centered, and this explains why at low temperature there is a very fast Boltzmann equilibrium among different excited states, but as soon as we start to increase the temperature, we are going to populate a non-radiative excited state that explains why we are at room temperature, we are a cluster with a very low, let's say, quantum yield, a short lifetime. Let's see now an example of what we can do by playing with the ligand. So before we play with the composition of a kernel, let's look at what we can do if we play with the ligand. And for this purpose, I would like to show you this nice study in which we functionalize nanocluster with the azobenzene thiol ligand, so with this very famous photoswitchable moiety, again characterized by quite long alkyl chain here to reach the core. So this is the structure, let's say the cartoon of the structure, but it was well characterized. And then we proved that even if the azobenzene moiety is its link is anchored on the nanocluster, it's still possible to photoswitch the azobenzene moiety from the trans to the cis, and then back to the thermally back to the trans original form. So if there is this cluster, the activity of the azobenzene molecule is still present, and we can photoswitch for several times this unit. And as soon as we look at the emission properties of the cluster, we observe again very nice near-infrared emission, for instance here if we excite at 600 nanometer. And then we wonder if we can play with the trans-cis form of the azobenzene molecule to obtain an energy transfer processes between the ligand, the photoswitchable ligand, and the core of the cluster. And to prove that, we need to actually modify our setup, because the photoisomerization of the azobenzene moiety is too fast to be observed in a different setup compared to the spectrofluorimeter. And so what we did, we modify our spectrofluorimeter to read simultaneously the photoluminescence and the absorbance by means of optical fibers, actually. And what we found out that the transform is able to induce an energy transfer between the ligand and the core of the cluster that indeed is higher emit compared to when the emission of a cluster where is in the cis form. And it was also able to repeat this energy transfer processes between the trans and gold of a cluster several times, as you can see here in this nice plot. So it's a selected energy transfer processes between the transform linked on the metal core that instead is not possible as soon as you switch the azobenzene cis form, but you can go back and repeat the cycle different time. So again, this is an example of the first, I would say, example of energy transfer processes induced by applying switchable behavior of a ligand covered the nanocluster. And what I really like to advertise, I would say, the possibility to use this nanocluster not only by atomically precise structure by itself, but also to use this structure like a nanocluster building block to assemble higher structure and to use this molecular structure and orderly structure for different kind of application. Nowadays, the scientific community is very is hardly work on the possibility to use this kind of material for catalysis and also for bioimaging or biomedical application due to their optical properties. And then I move to the last part of my talk, and here we like to show the possibility to, let's say, not use anymore an atomically precise control on the synthesis of a nanostructure, but again, to possibility to play with the supramolecular assembly and assembly of molecule to create bright nanoparticle. And in particular, I would like to talk about now, together with you, on a special case of dye-doped silica nanoparticle. In particular, during my PhD and postdoc period in University of Bologna, in the Luca Prodi group, we optimized a novel one-pot approach, synthetic approach, to obtain this kind of doped silica-core PEG shell nanoparticle. And basically, we took advantages of this dye-block polymer, the pluronic polymer, to create a sort of micelle in a water solution, and this micelle acts like template to synthesize in the core the core of silica, and which is possible to trap different kind of dyes. So we can basically trap spontaneously different kind of dye if we are more hydrophobic, or we can easily modify the dyes with this triethylsilane derivatization to really anchor it inside the silica core the dyes. And then by using a very easy approach of purification like ultra dialysis or centrifugation, we can purify the dye-doped silica nanoparticle and then obtain very highly stable water-soluble nanoparticle that, even if, as I say, are not anymore atomically precise, they are in any case characterized by very narrow distribution, as you can clearly see here by look at the dynamically scattering analysis and TM analysis. And particularly by combining these two morphological analyses, we can estimate an average hydrodynamic diameter of around 25 nanometer and a silica core inside of about 10 nanometers. So we are going, let's say, before atomically precise nanocluster of around 2 nanometer to one order of magnitude higher nanostructure that are not anymore atomically precise, but allow us to at least increase, as I show you briefly, increase the quantum and increase the total brightness of this system. And in particular, with this novel approach, we were able to obtain different kind of dye-doped silica nanoparticle, different kind of color with the same structure in terms of nanoparticle, but with different kind of dyes, sort of rainbow of color of doped silica core PEG shell nanoparticle. And then we were actually wondering how much we can dope this silica nanoparticle. So how many fluorophore we can place inside in order to increase the brightness of this system. I would like to remember you that brightness is actually the estimation of the absorption and the emission quantum mil of the dyes. So we were wondering if we can at least load as much as we want the silica nanoparticle in order to increase the brightness of the system, or if there are some limitation. And to prove that, to check this, we actually synthesized this family of nanoparticle with the same size, with the same core and the same shell, and doped with an increased amount of rhodamine dyes that we use as probe because its photophysical properties is well known. And as you look at the absorption of this family of silica nanoparticle, you can clearly see that there is an increase of absorbance and a sort of linear increase in function of the doping, of a loading effect. But as soon as you look at the emission, and in particular the emission of a nanoparticle, their lifetime, and also the emission anisotropy, we observe that actually there is an increase in the brightness of a system up to 10 rhodamines for nanoparticle, and then the brightness dramatically decrease. And we wonder why this happened. Basically, we discovered that inside our Silica-core there is actually very fast energy energy transfer among different rhodamine, active luminescent rhodamine. But as soon as we start to increase the loading, there is aggregate effect among rhodamine inside the Silica-core, and this aggregation is well known that are characterized by a lower excited state that acts as a trap of the emission, and this determines the decrease of the fluorescence as soon as we start to increase the loading of rhodamine. And so we thought about a strategy to recover this quenching effect, so how we can recover this effect to actually increase the brightness of this system. And the solution that we found, I would say the smart solution that we found, is to use a red-emitted acceptor, energy transfer acceptor, like a Chi9. Like this is not hydrophilic. Also, as soon as we start to add this cyanide inside our water solution with nanoparticle, it tends to go through inside the peg of the silica nanoparticle and stay there trapped, because it's, of course, for hydrophobic reason. And as soon as we trap cyanide inside the peg, this activates another energy transfer phenomenon between the monomer, the aggregate, and the lower emitted cyanide layer, and this this actually acts like a final acceptor of this energy transfer phenomena, and that could help us to recover the quenching of the brightness that we observed before. And indeed, if you look at the trend of the brightness upon the addition of the cyanide in the PEG cell, you can clearly see that we can increase as much as, let's say, we want the brightness of this silica nanoparticle, dye-doped silica nanoparticle. So once obtained this result, so we are actually able to modify the silica core as the PEG shell as we want to optimize the luminescent properties of this system, this nanoparticle, and we place this with this same kind of structure to obtain tandem dyes. In particular, we select a sort of cascade, different kind of dyes with different energy level in order to optimize the energy transfer among them. So a coumarin, bodipi, rhodamine, cyanide, all trapped inside the silica core in order to obtain energy transfer among dyes trapped inside the same structure. And as you can see here, like a final result, basically we can tune the absorption spectrum of this silica nanoparticle, and we can actually tune the emission properties of this doped silica nanoparticle just by playing with the different of dyes that we trap inside. And so we were actually able to obtain a very nice tandem dye with a very also stock shift, if you consider that here we can excite a 400 nanometer and obtain an emission in the last case at 700 nanometer with a very high efficiency in energy transfer processes. So just before conclude, we also use this kind of approach to enhance the performance of this silica nanoparticle. In particular, if you think about bioapplication in which you want to use nanoparticle like labeling, the best condition is to have a readout of a signal, so the emission signal that is not connect with the input. And one of these more elegant way to obtain this result is to use the electrochemical the ECL approach, in which you can use the formation of excited state of your dyes by means not anymore of an optical input, so not by means anymore the excitation of the dyes, but by use of an electrical chemical input. And this actually is the scheme that standard scheme that we use for ECL in the case, for instance, of a ruthenium like Luminescent probe. So we use the same kind of approach with our dye-doped silica nanoparticle in order to again have fluorescence emission without photoexcitation, and so to increase the performance of this kind of silica nanoparticle. And this was one of the first our achievement, in which we dope our dye-doped silica nanoparticle with an iridium complexes. It's one of the well-known ECL active probe for this kind of approach. We dope the nanoparticle, the silica nanoparticle, with the ECL probe, and basically we apply the ECL approach. And what we observe, as you can see here, is the ACL intensity of emission of the iridium inside the silica nanoparticle. And so by means of this approach, we were not only able to see an ACL emission, but we were able to obtain ACL emission by in a water solution, because otherwise iridium complex is hard to solubilize in water. Instead, in this case, we can trap high number of iridium complex inside this water soluble and highly stable structure, and so we are able to not only optimize the ECL signal, but also to have an ECL probe that can be easily, that is stable and for a long time in water. And we use the same kind of approach to obtain energy transfer ACL probe. In this case, we use the same kind of structure, and we dope it with 3 different kind of ACL active probe, diphenylanthracene, rhodamine, and cyanine, in order again to have a high efficient energy transfer among these different free dyes from the blue emitted white through the red emitted one, the cyanine one, and we use the same kind of ACL approach to tune the emission in the ECL probe mode. And so we control the final color of emission by means ECL, so again without use of excitation. Basically, we use this kind of silica nanoparticle, different kind of application and with different kind of purpose, and we in all of them fine control of the structure and of the doping of the class and the doping of the dyes inside the silica was the exact way to obtain and to increase the brightness of the final emission signal. With that, I would like to thank all the group where I work, starting from my group in which I performed a PhD in Bologna, of course my mentor, Professor Luca Prodi, and also all the other collaborators. Then the group in Strasbourg, Paolo Samori group, where I performed all the study of 2D material and photo-switchable 2D material. And then, of course, my group now, where I'm research assistant in Padova, the group of molecular electrochemistry and nanosystem group led by Professor Maran. First, Before to conclude, I would like to advise all the master students in your research center that there are some very interesting open positions for PhD. So if some of you are interested on the possibility to do a PhD in Italy and in France at the same secondment period, working on electrophotoCatalysis based on metal complexes for catalyze small molecule like CO2. If you are interested, please write an email. And as well as if you are interested on cluster or metal cluster, please don't hesitate to ask me for curiosity or for collaboration. And with that, I would like to thank you for your kind attention, and I'm here for questions.
Thank you very much, Sara, for this inspiring presentation. I think you took us across from different topics, interesting all of them. So now we will open the session to questions. Vamos a pasar a la ronda de preguntas, a la sesión de preguntas. Si alguien tiene alguna pregunta, ya saben la dinámica, lo puede escribir en el chat o bien me indican si quieren preguntarle directamente a la doctora Sara. ¿Alguna pregunta del público? ¿Alguien tiene alguna pregunta?
Or curiosity is, of course.
Yeah. Question or doubt or comment also is valid.
Yeah. Actually, I cannot see you, all of you, but I mean, it's fine.
Okay. So Sara, for instance, in the when you talk about these precisely controlled metal nanoclusters, and you mentioned something about these sensing strategies, or how to control, for instance, this thermometer, or the cluster they use for the thermometer, or a nanothermometer. Are there other applications foreseen for these type of precisely controlled metal nanoclusters?
Yeah. Nowadays, I would say, this for this atomically precise nanocluster, the most promising application are basically on biomedical application, since they emit in the near infrared vision. Even if, like that, it's hard to have the same kind of atomically precise control in the synthesis as soon as we start to deal with hydrophilic ligand, So if you want to play, of course, with bioapplication, you should have something that should be water soluble or at least very polar. And that makes some difficulty in the synthesis of these structures. So they are not as stable as the one that you can obtain when you use thiol or carbene or phosphine ligand. So one approach could be like the one suggested by Acknowledgements or other big group working on this atomically precise nanocluster, is to use the combination of this cluster to get the protein. And so play with this, let's say, big structure and place the cluster inside protein to target your bio target in vivo or in analysis. Another kind of application instead is on the catalysis. Of course, as soon as you reduce the size of gold, you increase the catalysis performance, or at least you should increase the catalysis performance of a structure. I think it's very promising application, even if till now most of the more important results are actually, if you look at with attention, most of the time you see that the clusters are actually used as a catalyst but supported by other material. So it's not real homogeneous catalyst, but you use cluster for optimize the catalytic active active substrates, you see. And so I would say there are a lot of open possibility for this cluster, but we have to be very careful in the synthesis and the stability. And if I had to be honest, I also for real application, I would say that I will try to change the metal core from gold to other cheaper material.
Yeah, that's something I see that you're starting to work with now. No? Copper, for instance, getting away from gold and going towards cheaper materials or transition metals instead of noble metals, right? That's a promising approach.
Indeed, there are very, very interesting atomically precise cluster made of transition metal decalcogenide that they show very peculiar electrical properties, but I don't know how about their so electrical properties. Yes, they show peculiar electrical properties like molecule, like the one I showed you before for a gold nanocluster, but I don't know what about their properties on optical properties actually. I don't know if they can show.
Okay.
Especially for your institute, for this. For your
and for instance, for the last part of your topic, this silica nanoparticle top with dyes, I see that you can control all this energy transfer and you can modulate eventually the emission color, right? That you can have like a combination of different emitters, let's say, present in your sample. You actually can tune this very well. So for other types of application, let's say, I know that, for instance, competing with this phosphorus or lighting will be difficult, but for instance, for, this precisely designed OLEDs, because you are using now electroluminescence, right? I mean, combination of this. So have you, for instance, tried to, put this in a kind of a device and architecture to have this type of devices?
Basically, we never try because compared with the state of the art in that field, I don't know if there are very more, and in the Luca Prodi group, we are still focused on bio application because actually the peculiar thing of this kind of structure is that they are really water soluble for a long time, and you can play to that with the possibility to tune the emission up to near infrared emission, where usually only organic dye, not water soluble, emit. So the power of this kind of structure is the possibility to have water soluble and at the same time play with the color. And the same thing if you think for instance of quantum or similar structure is not as easy as in the case of silica nanoparticle, obtain the same water stability and the same tunability in color. And so instead for OLED or so on and so far, I don't know if it can be really competitive, I would say.
Okay. Thank you, Sara. So we have a question from Luis Fernando Gomez Caballero. First of all, he wants to thank you for your talk. It was quite interesting. Another question is, have you worked with metallic cores and then attach fluorophores or dyes with silica to them? It's kind of a combination of both of.
So basically, there are famous, I would say, example, if you think of Akovitz, of metallic core surrounded by silica core to have an enhanced emission. So you have a metallic core and ran a silica nanoparticle doped with the dyes to obtain enhanced emission. But are still not in, let's say, not atomically precise field, you know, so still a sort of size distribution. Combine atomically precise cluster with silica could be hard from a synthetic point of view, because even if it's true that we can really play with the ligand to modify, with the ligand, so make the so-called ligand exchange to change the dynamic surround around the metal core. It's not so easy to be sure to maintain the same kernel. So from synthetic point of view, it could be hard to combine atomically precise nanocluster and silica structure. And also for purpose, so if I think about application, I don't know if it can be useful. So I mean, we are working, for instance, of to combine dyes with covalent link with different kind of atomically precise classes to play with the electron transfer or energy transfer, for sure. But I don't know if it can be convenient to attach silica nanoparticle to atomically precise cluster. I think we can play with different kind of superstructure for the purpose. I don't know if I got the question actually.
Thank you very much, Sara. And that's something that's very interesting, you know, because recently there is this controversy, or well, just like dispute, let's say, because I've seen passing some papers about, you know, at what time or at what moment these kind of precisely controlled nanoclusters become a nanoparticle, right? Because like there is like a boundary between plasmonics,
so
you know.
Till some years ago, we thought that 45 was the boundary, was the limit cluster between like the atomically precise and plasmonic nanoparticle, let's say. Now the sizes are increasing, so we are like a big cluster, and there are like a lot of research groups that are really working or really focused on find the line between a really precise cluster and nanoparticle. For sure. Sorry.
Yeah, I saw this paper from a University of Cannes in France last year saying, like, you know, this kind of atomically precise nanoclusters, if you have them confined, you know, into a structure, porous structure, for instance, they can behave like a plasmonic nanoparticle, something like that. I'm still not really convinced, but okay, the question is in there, you know, the topic is in there. So we have another question, Sara, from Mario. He thanks you also very much for the seminar, and he would like to know, how long does it take to photo-reverse the color in the organic molecules of the first topic, or at what temperature is needed to photo-reverse the color? I think that, I don't know if it's...
Yeah. Okay, I got it. So, sorry, I don't know if... Yeah, okay. So we are talking about the ability to use spiroparine molecule to tune the electrical properties of 2D material, basically. I'm going there. I have also, So, okay, since we are working on dry film, of course, is longer compared to the photo-switchable behavior of spiroparine in solution that actually are very quick. So it's depend on the event, of course, but spiroparine are usually very fast to switch back and forward. We did all our experiment in dry, so we spin coated our solution, our colorful solution contains spiroparine on top of this 2D material. So here I have, for instance, here I have a timing. I don't know if you look at the are like 1,000 minutes to go back, but this is the timing for bulky, let's say, so for the thin film. But if we look at the switching that is necessary to the time that to wait for tune the 2D material are quite faster. Usually to go from spiral to meracynin, we just need like UV LED for a few minutes. In the paper, the power of irradiation and timing, so all the detail. And we sometimes to speed up we warm up for like 30 degrees, no more, in order to avoid any kind of modification of a structure on top of a 2D material. So it was very fast, it was actually very fast to observe this kind of photo-switchable behavior, even if we were working on dry film. So I don't remember exactly the timing, but for technical, let's say, data, you can find everything in the paper. So power, LED, timing, and temperature to play with the back thermal isomerization.
Okay, thank you very much, Sara. And again,
yeah.
Mario thanks you for the response.
Yeah, thank you very much.
And again, I would like to thank you for accepting the invitation for this very nice topic.
Thank you, really.
And we keep in touch. Sara, have a nice weekend. Yeah. Thank you again.
Yeah, you too. Thanks again. Yeah. Thanks.
Gracias a todos. Buen fin de semana. Hasta luego.
Yeah. Ciao, grazie.
See ya.
Ciao, ciao, ciao.